Good day. This is still AP Chemistry, and it is still topic 2A within Unit 2, or Big Idea 2 for AP Chemistry. We're going to just look at solutions for this screencast. Solutions are homogeneous mixtures and are composed of a solute and a solvent. They can be gases, liquids, or solids. For a liquid solution, the solute can be a gas, liquid, or a solid. In solutions, the solvent particles are very tiny, molecular size, people. Like a solution, a colloid is a mixture of two separate phases, but where the particles are larger in size than molecules, up to approximately 1,000 nanometers. If the particle size exceeds 1,000 nanometers, the mixture becomes a suspension. As in not suspended from school, a suspension in a solution. These particle size distinctions mean that a mixture can appear homogeneous or heterogeneous, depending on the scale on which it is observed. For example, with the naked eye, a colloid, like an emulsion paint with a solid dispersed in a liquid, looks homogeneous, but on a hugely magnified scale it may appear heterogeneous. Liquid solutions, by definition, cannot be separated into their components using a filter paper and have no particles large enough to scatter visible light. Two such methods that can be used to separate such solutions are chromatography and distillation. Chromatography. All chromatography techniques involve a moving phase and a stationary phase. In the most common applications of paper chromatography, the paper is the stationary phase and the solvent is the moving phase. When the solution mixture is exposed to the two phases, each component of the mixture will have a greater or lesser affinity for the stationary or the moving phase. If a component of the mixture has a high affinity for the mobile phase, meaning it has a high intermolecular attraction for the mobile phase, it will move with the moving phase and travel a relatively long distance on the chromatogram. A component with less affinity for the mobile phase, low intermolecular attraction for the mobile phase, or only an affinity for the stationary phase, strong intermolecular attraction for the stationary phase, will not move as far. The different distances of travel mean the components of the mixture are physically separated. It is possible to apply quantitative analysis to the chromatogram by calculating an R sub F value. So the R sub F value is the distance traveled by component of mixture divided by the distance traveled by the solvent. Chromatography. The distance traveled by the solvent is determined by measuring the distance from the baseline, where the original mixture was spotted, and the maximum distance that the solvent has traveled, known as the solvent front. So here's the solvent front. So this piece of paper or TLC, whatever it is, was put in probably some kind of solvent like alcohol, maybe water, and the solvent line was up to there, and this mark is where maybe the ink or grape Kool-Aid, something was put on it. And as the solvent was pulled up through the paper or the TLC, it carried some of the components, maybe the ink, because ink is made up of different colors of ink, up here, and then it stopped here. That's the solvent front. So that's the distance traveled by the solvent all the way through there. And see, it does carry some things with it that are attracted to it. Distillation is a simple separation technique based upon differences in boiling of two components of a mixture. The boiling points, I should say. The boiling point of the individual component of a mixture depends upon the intermolecular attractions between the particles of that component. For example, ethanol molecules have a relatively low intermolecular attraction for one another when compared to the intermolecular attraction that exists between molecules of water. Because the ethanol molecules have a relatively low attraction for one another when compared to the water, they are relatively easily separated from one another, and they have a relatively low boiling point, 78 degrees Celsius. Because the intermolecular attractions between water molecules are greater, they are more difficult to separate and have a relatively high boiling point, 100 degrees Celsius. As a result, a solution composed of ethanol and water can be separated by heating the mixture. The ethanol molecules, with a lower boiling point and a weaker intermolecular attraction, vaporize before the water molecules and can be collected as a vapor and then cooled to condense them back into a liquid in a separate container. The water molecules do not vaporize as easily and are left behind in the original container, and thus the mixture is separated. This process of separation by utilizing different boiling points is called distillation. Hence, people making moonshine, they were actually distilling, and they were probably trying to get the pure alcohol out of the mixture. dilutions. We covered these last year if you were in first year chemistry. M1V1 is M2V2, or if you want to call it MAVA, meaning molarity, acid, volume. Acid equals the molarity of the base, the volume of the base. The gist of it is the moles you had before equal the moles afterwards. It's just the concentration of the solution and the volume of it change. So just note that volume 2 is the total volume. To find volume 1, you may need to subtract from the total volume. For the AP test, be able to describe how you would make a diluted solution. Your verbiage should include the use of highly accurately graduated glassware, volumetric flasks, graduated glass pipettes, and burettes. So, for example, add approximately 1 liter of water to a 2-liter volumetric flask. These are the flasks with long necks and one line on it to accurately mark a volume. Using a suitably sized pipette or burette, slowly and carefully transfer 0.75 liters of the concentrated solution to the volumetric flask with a gentle swirl to ensure good mixing. When all of the concentrated solution has been added to the flask, make the solution up to the mark in the 2-liter volumetric flask. It means add water to the 2-liter volumetric flask. Remember to add acid to water as you otter. So if you add water to acid, when the water goes in there, the acid may splash out and may get on you and burn your skin. But if the thinking is if you add acid to water, what is going to splash out is the water parts, and that's not going to hurt you. Dilutions and safety. So when diluting a concentrated acid or base, it is often found that combining water and the acid or base is a very exothermic process, meaning heat is released. You would feel the container getting warm, perhaps quite warm. Example, one that releases energy. So in some cases, this energy can be very significant and may cause the water present to turn into the gaseous state or steam. I've seen this happen. As the steam leaves the system, it can cause a spray of concentrated acid or base, and as such, it represents a significant safety hazard. In order to minimize this hazard, it is important always to add acid to water and not water to acid. The dilution sequence of adding a relatively small amount of hazardous acid to a relatively large volume of non-hazardous waters ensures that the heat generated is kept to a minimum and that acid remains in the presence of as much water as possible until it reaches the desired dilution. This will minimize the risk of accidents. So here's a problem you might see for solutions. Calculate the volume of water that must be added to 2.75 molar sodium hydroxide in order to produce 150 milliliters of 2 molar sodium hydroxide. So I'm looking at it, I'm going from a concentration of 2.75 to 2, and my total ending volume is going to be 150. So I'm going to start with a certain amount, and then I'm going to have to add to get to that. So you could use M1V1 as M2V2, and so the molarity one is 2.75 moles per liter times the volume one, which we don't know what volume one is, equals the second molarity, which is 2 moles per liter, and we know the second volume, which is 150 milliliters. If we solve for V1, we get 109 milliliters. So that's how much volume we're starting out with. So how much are we going to add to that to dilute it to 150 milliliters? So you'll go 150 divided by 109. You'll add 41 milliliters to produce a solution that is 2 molar, and there's 150 milliliters of it. So will the diluting be exothermic or endothermic? Exo means usually hot, endo usually means cold. Consider a substance dissolving in water. 3 separate independent processes must take place, each with its own associated energy change. So 1, the solute particles must separate from one another. Bond breaking process, endothermic people. You have to put something into it to break it. The solvent particles must separate from one another. Bond breaking process, endothermic. The solvent and solute particles must interact. Bond making process, usually exothermic. The energy change of the overall process is a sum of energy changes 1, 2, and 3, and can be exothermic or endothermic depending on the magnitudes of each. It tends to be when you're making solutions, most of them are exothermic, not as many of them are endothermic. That concludes our solution part of topic 2A for the big idea 2 for AP Chemistry. Until next time, add 'em up.